Welcome back, Professor Bright here, and we are going to be now looking at combining the use of exponential functions and logarithmic functions as we turn our attention towards solving equations. And so the first type of equation we're going to look at is an exponential equation. We kind of been dealing with these in different ways, but some of them have been easier for us to solve, others have not been so easy. And so we're going to kind of focus on both types here. So to begin, we're going to see this first example on the left here. We have 5 as a base, and then the exponent is 3x minus 1. And on the right side, we have 25 as the base, and the exponent is 2x. And so how we kind of solved this before is we said, well, if we can get to same bases on each side, then we are going to be good. And so I recognize that 25, I think of 25 as 5 squared. And so I can just write this as 5 squared to the 2x power on the right and just leave the left-hand side alone. And then now, continuing my work, ideally I want to see it as 5 to a base, and the left side would just have the exponent of, 5 to an exponent, the exponent would just be 3x minus 1. On the right side, I have a base of 5, but then I have to resolve the exponents. Remember that if we have exponent to exponent, we end up multiplying the exponents. So then this would be 4x, not 2 plus 2x or anything like that. Okay, and now I can say, oh, all right, I have the same bases, and so I apply that injective property of exponential functions and say that the exponents must be equal. So I can come down to the next line and say 3x minus 1 is equal to 4x, and then subtract 3x from both sides. So I get negative 1, and I guess I'll show that work, minus 3x, and I get negative 1 is equal to x, okay? And so that would be my answer. And certainly I could substitute back in and check. We actually don't need to check our answers with exponential functions, but we always could, just to verify that, yep, this is the right answer. Next problem, okay? I have 4 as the base of an exponential expression, and then that has a power of 3x minus 2. All of that is minus 7, so that's on the same level as the base, and then that's equal to 2. So generally in solving these types of equations, what we want to do is we want to isolate that exponential expression. Okay, so I'm going to add 7 to both sides. Okay, I'd get 4 to the power of 3x minus 2 is equal to 9. And now at this point, I'm stuck. There's no way that I can write 4, a base of 4, and a base of 9 in the same exponential. Okay, so this is where I cry a little bit, and then I pick myself up and move on, and I say, oh, I remembered about logarithms, right? Logarithms are a way to get at the exponent in an exponential expression. And so I'm just going to switch this to logarithmic form. And so remember, with logarithms, I have to practice the tattoo or use the circle method and say, okay, I'm going to have a log with the base of the exponential, and inside the logarithm is going to be the opposite side, the output, is equal to whatever our exponent is. So the logarithmic form here would be log base 4 of 9 is equal to 3x minus 2. And then if I want to solve for x, I would just need to isolate it, so add 2. This logarithm base 4 of 9, that's going to be a number. We could use the change of base formula to calculate it. I don't much care what it is right now. I just want to get at x. So this is equal to 3x. Divide both sides by 3, and then get log base 4 of 9 plus 2, all divided by 3 is equal to x. And that is my answer. Okay, so 2 equations that we saw here, we could try and use the injective property of exponential and logarithmic functions. So again, if you have same bases, then the exponents must be equal. That's what that property says. And you could do the same thing with logarithms, right? The other equation that we saw, the other exponential equation that we saw, required us to isolate the exponential, and that's always a good strategy if you have just one exponential occurring, and then switch it to logarithmic form via the tattoo or the circle method, all of which is just a fancy way of saying the definition of a logarithm. Okay, and so in general, the second example that we saw actually includes the generalized approach. And so what I recommend first is always try to isolate the exponential. Okay, in the first equation that we saw, the base 5 and base 25, I couldn't do that because I had exponentials on both sides. So if that's not possible, then you're going to probably end up using the injective property. After you isolate the exponential, what did we do? We switched to log form. Okay. Now, at this point, you could do something different, and you could apply a logarithm on each side, apply a log on each side of the equation. And which log you apply is completely up to you. You could use natural log, common log. You could use, in this example here, I could have done log base 4 just so, you know, the base 4 of the logarithm and the base of the exponential would cancel each other out. Okay, so that is up to you. And then third, after you've done that, you're going to simplify for sure and solve for x. And that is the general outline of a way to solve an exponential equation. So let's get some more practice here. Okay, I'll try and leave those on there, at least in part. All right, so first thing, I want to isolate the exponential. So there's the exponential. I know it's an exponential because I have a base and I have an exponent, so I want to isolate that. So get rid of the 4. E to the 4x minus 1 is equal to 13. And then now, I could switch it to log form. I am going to do something different. I'm going to try this applying a log on each side of the equation just to illustrate what that looks like. So when I say that, I might say, let's do a natural log on both sides. As a mathematician, I am trained to always do natural log. I don't know why we do it. It just ends up being nice in many applications. You could do common log to log, totally fine. And so here, when I isolate when I apply a logarithm, right, I can use log properties, bring that 4x minus 1 down in front, and then I'd have natural log of e is equal to natural log of 13. And then it so happens to be that I chose a nice logarithm here because natural log of e is just 1. So the left hand simplifies to just 4x minus 1, that quantity, times 1, or simply 4x minus 1 is equal to natural log of 13, which is coincidentally the same thing you get using the circle method or the tattoo. Finish solving by x by adding 1 and dividing by 4. Okay, so there you go. All right, so there's one example. Now, this last example is perhaps one of the most difficult types of equations where you have exponentials on both sides and you need to solve it. Okay, so what do? Okay, the answer is cry a little bit, always. But at the end of the day, there's no way that you can isolate the exponential. So then you kind of have to skip that and just say switch to log form or apply a logarithm on each side. So in this case, let's try switching it to log form. Which one is the base of our logarithm? The answer is it's up to you. I'm just going to do this one. So I'd have log base 3 of the other side, 2 to the power of 4x minus 1, is equal to the exponent, so 5x minus 6. Okay. And then what do? Oh, okay, so I have to simplify the left-hand side, right? So it says simplify. So use properties to bring that down in front. So 4x minus 1. That quantity times log base 3 of 2, okay, is equal to 5x minus 6. Now, my goal is to solve for x, but the problem is I have x on the right side and the left side. So I have to go through some algebra, right? This log base 3 of 2, that's just a number. So think of it as another number. Let's call it right now. Let's call it capital A. If that's a number, that can be distributed. So I'd have something like 4a times x, all minus 1 times a, which is a. And then this is equal to 5x minus 6, okay? And then now to solve this, right, I need all the x's on one side, all the non-x's on the other. Okay, so then I'd have, let's see, 4ax minus 5x. So I move the 5x to the left-hand side, and the right side I'd have positive a minus 6. And then now at this point, in the left-hand side, both terms have an x, so I'd have to factor that out. Oops. 4a minus 5 is equal to a minus 6. And again, a is representing log base 3 of 2. And so then dividing here, I'd have a minus 6 over 4a minus 5. But really what that's saying is a is the number log base 3 of 2 minus 6 over 4 log base 3 of 2 minus 5. And that would be my answer, okay? And yeah, the answer has a logarithm in it, totally fine, because the logarithm, as long as you have all constants in there, it's a number, okay? And to find that number, if you really need to, use the change of base formula, okay? But for now, we're gonna leave our answer like that because that is the most exact answer that we can get right now. All right, so in this video, we looked at solving exponential equations. First couple were some easier archetypes where we have same base exponentials on both sides, or we can at least get there. The next archetype we saw was one where we could isolate an exponential, which is going to be most of the cases. And in that case, we had to switch it to log form, which we saw in the next example. Okay, and then when you switch it to log form, you also have to solve or simplify and solve. This last type is the most challenging, where you have to apply a logarithm or switch it to log form and then carefully carry out some algebra that follows. Okay, so make sure to review that last example carefully, and we'll get some practice with it in class.